Hello everybody and welcome to the last CS 302 online this semester. Hello there, General Kenobi. Were you looking for me? I hope everybody's doing good. We got a couple of people now. I was worried. It still says that there's one viewer, so who knows how many viewers we have, but there's definitely more than one, so that's good. All right. I'm going to assume that the audio works fine this time because otherwise people would have panicked by now. So we are good. Don't feel bad. I guess if you're taking 219 with me in the summer 3, I'll see you then. So it shows 39 on your end. Okay, that's much better than 1. So good. Okay. Well, we got a lot to cover, so we're gonna get started as soon as possible. If you have, that looks interesting. Okay, I did mess around with the settings so that the background looked nicer, but I guess it had a side effect. But are we getting balanced streams during the summer? You're gonna get CS 135, CS 202, and CS 219 streams during the summer. That's what we're gonna be getting. I don't know if we're gonna get balanced streams during the summer. We'll find out. But I am teaching all those classes through Twitch, so we'll see how that goes. And then yeah, sure, we'll play some Valorant. If you guys got Valorant, you know. It's the last one. What's the worst that can happen? Maybe we should I was gonna say we should turn Valorant keys on, but no, everybody has a key by now. So, okay then. I don't want to get too distracted. We gotta get going on this. After I finish the lecture, then we can hop on and talk a little bit about the test, about the assignment and other things, and say our byes and whatnot. I mean, the class is over in terms of lectures, but you do have your test tomorrow, from 12 to 12, and you have the final project as well, too. So the class is not necessarily over. It's just the lectures are over and they get to tear down all my setup and upgrade it, hopefully. So let's get going now. All right. Yes, it did. However, it is still worth the same % of your grade. So there's going to be some people said like the people wanted less points in test and I gave them less points. So there it is. And I do recommend you watch the Tuesday lecture for the final because I did the lecture and then I did the final. So I pretty much based it off of what I said, as I said I would. So yeah. Okay. Let's jump in for the last time to the iPad. All right. So this is, as it says there, the final ever online live stream for this semester. We are going to be talking about new subjects today, of which there will be 1 or more questions on the test. So they're not going to be that hard, but let's put it this way. Without watching the lecture, you may miss it. So you definitely want to check this out. Okay, so this is going to really wrap up very well this semester, this lecture. And we're going to be talking about algorithm analysis and then kind of segue and introduce into the NP completeness and P versus NP. All right. So let's talk about algorithms. And if you have any questions about the test or about anything else that's not related to the lecture until after the lecture, okay? You can ask questions about what I talk about, just not other stuff, because I really want to get this done because I know some people have class and I don't want to go on for 2 hours because with the stuff that's going to be on a test tomorrow at the very least. So that's why, okay? But yeah, people on the chat are right. Yep, last lecture was indeed the worksheet. So, okay, let's talk about algorithms. So what is an algorithm? Back to CS 135, hopefully they gave you an introduction about what an algorithm was. And if not, then I'm sure by now you have a pretty good idea of what it is. But let's go ahead and kind of revisit that definition and maybe expand on it a little bit. And so here I have the most basic sort of image that I can think of when I think of an algorithm. And of course it comes to me in the idea of a meme, you know, those memes that say like how to make a nuclear bomb. Step 1, I don't know, buy some metal. Step 2, weld metal. Step 3, question mark. And then step 4, like profit, right? And so at that point it's like, okay, that's a big step, right? Or like those cooking videos where like, it's like, yeah, cut the onions. And then like, the next step is like insanely big, and then it's like eat the food, and you're like, what? That's kind of typically when you think of an algorithm, you're thinking of that big step in the middle, right? So you're feeding it something in, it's doing something, and then you're getting hopefully something good out of it, right? So for example, in sorting, you feed it in an unsorted set of data, it sorts it, and then the output is a sorted set of data, right? And so how it does it, those are going to be the steps, the rules, the formulas, and in terms of programming, that's made up of all the if statements and functions and all that great stuff that you guys have been coding all semester long. And so that's basically what an algorithm is, right? It's all these steps and rules that are converting, in a way, your input. They're mutating it into something you want, right? And don't get it confused, because there were two big things that we talked about this semester. We talked about algorithms like Dijkstra's shortest path and minimum spanning tree and sorting and some, maybe not fully searching. I mean, we kind of touch into binary search, but we talk binary search trees, so that's useful for searching. But we also talked about data structures, right? Data structures like a hash table and things like that. So not necessarily all the algorithms, all the content that we talked about was algorithms, right? So I'm talking about the algorithms being that feed into this process. Now, for you to go from what is necessarily here to here, you may need more than just an algorithm. You may need a data structure to hold the data while you're processing it, such as a tree when you're doing an ABL tree, right? Or hash table when you're doing, well, hashing is not much of an algorithm, but sorting, you got to store the data somewhere when you're doing merge sort, so you could use an array, or you could use a linked list. I mean, you did it in all three different ways, right? You did it with vectors as well. When it comes to minimum spanning tree or Dijkstra's shortest path, there are many ways to store that, as you saw in assignment 11, and now you're seeing in 12 if you're using Dijkstra. You can use an adjacency matrix, you can use an adjacency list, you could also just keep it all in pointer. So there's more than one data structure for a certain algorithm, and now I want to focus on the algorithm part of that. And so the summary that I put here is basically saying that it's a system of rules, states, and transitions used to convert something that you're giving in into output. And something else in computer science shares that sort of definition, and that's going to be a Turing machine. So what's a Turing machine? Well, I'm going to very briefly touch it, and if you want to know more, you can. There's when you take automata, they will talk about it in detail. But ultimately, it does two things. It decides formal languages being a subject in computer science that will be visited quite in detail in a couple of classes, and also it can solve mathematical functions. And a Turing machine is nothing more than a little. You can think of it like, well, I have a picture that I try to draw here. You have two rolls that maintain magnetic tape, or any sort of tape actually, with little holes or something in it. And then you feed it into this sort of scanner that processes the tape. And it doesn't even have to be a scanner though. I mean, you can make a Turing machine out of like wood blocks almost per se. And ultimately what that looks like, more of a easier way to understand it, is you have your input symbols, and then there's a couple of rules, grammars, or steps there, which are your algorithm. And then at the end of it, you have accept states or end states. It's an accept state if you're talking about a formal language. And if you reach that accepting state after you feed it in the language, then it means that what you fed it in is actually part of the language and it's valid. In the terms of a mathematical function, the end state means that when you reach that, you see what the Turing machine has like sort of stored or saved, and that's going to be your output to your math equation. And that's pretty much all there's to it. This is actually the most simple form of I know, well, not simple in what Turing is, but the example here of automata and finite state machines, there are deterministic finite state machines and there's non-deterministic finite state machines, and I'll talk about that a little bit later. But ultimately, here's a good statement of what a Turing machine is. It's given in any computer algorithm, a Turing machine capable of simulating that algorithm's logic can be constructed. And so if you have any algorithm from this class, you could build a Turing machine that could do it. It's not going to be easy, but it's going to take a lot of work. Why is it forming a graph? Because each of these nodes you can think of accept states. And as you start from the left to the right, you're going to take that input and then modify it in whatever your rules require you to as you transition it into the final output. An example of a very simple, like a formal language is in the sense of like, imagine that I'm trying to generate letters, like an actual language, okay? And if you think of like tries and things like that, suppose that I accept, my language consists of accepting words that are like, that have letters A's followed by letter B's. So this is acceptable. This is also acceptable. This is also acceptable. This is not acceptable. And of course, this is not acceptable, right? Or this. Why? Because it has to be followed by a B. It has to be followed, it has to have at least one A and at least one B. And I can write a grammar that specify those rules. And again, I don't want to get too into that because there's an entire class that you're going to take on that. But ultimately, what you need to do is you need to create rules that can check whether such a grammar exists. And what that actually would look like for this system would be like, you have your input, and let's say that feeds it into an A. And well, I guess lowercase a actually. And then you have a little arrow that comes back to yourself. And then from there, it goes to a B. And then you have an arrow that comes back to yourself. And from there, you go to your accept state. And so you have your start state and your final state. And if I try to feed any sort of input to this, suppose that I want to generate a bad language, I can just follow this through, and anytime that I get to the end state, it's okay. In that case, it would be just AB. Otherwise, I could do like A again, A again, A again, here, B again, B again, B again, and then final, right? So all of these I could feed in. If I fed in something like just the A, then, well, the A takes me here, and then the next character I have is supposed to be the end of it, but I'm not in the end state, so that means that it is not acceptable, right? If I feed it A, B, B, well, I have an A, so I want to go to another A. I just go around. I can do that. Then I need to go to a B, so I can take it here. I need another B, so you go around. And then at that point, I can go to the accept state. Now, depending on this, you can make this itself the accept state, but then if you did that when you went to the A to the B, you don't have to print the B. So there's a lot more to this than what I'm showing you. And personally, I haven't seen this in a while, but this is kind of the most basic of it. You saw it in CPU 100. Oh, that's actually impressive. It is a finite state machine, yes. So why is it finite state? Because I don't want to spend infinite time drawing it. So the fact that I can draw it means that it's pretty finite. So yeah, but anyways, that's kind of the basics of what a Turing machine can do and is in a way. So ultimately, anything in computer science, in coding, like in programming, that you can code in a computer can be done with a Turing machine. Okay? So the question I ask you guys is, can a Turing machine solve anything or everything? Or are there things that a Turing machine cannot solve? And I'm telling you that a Turing machine can do everything that we can do in a program. So does that mean we can solve everything? No, you're right. It cannot. You cannot solve everything. And I have a whole bunch of things here that it can solve, but it kind of goes down into the most basic example is the decision problem. And there I have the original name, which is like Einstein-Dong problem. And so that's another name for that is kind of like the grader's problem. And so suppose that I'm asking for an algorithm, and that algorithm expects as an input a statement from you, and then the algorithm has to return yes or no based on whether it is universally valid or not. And so it's impossible to do this with coding, because you could code an if statement, a big nasty if statement to accept every single order of the words that I'm saying, and then you could like hard code that as an acceptable answer, yes or no. But there's an infinite amount of things that I could say. And so you're gonna have to code one for each one, and you would never finish, right? Another example of that is, suppose that I, as a teacher, wanted to create a program that would grade your assignments so that I could fire the TAs and not have any TAs. Because I could just like run it to my program and do it. And in a way, I mean, think about it. A compiler, like if a code compiles, then it runs, right? So it's basically like I'm creating a compiler that not just checks errors, but also checks like semantic stuff, right? And the answer is I cannot. And not even that like that in depth, but there's something that I have here about the halting problem, okay? Let me make you an even simpler example of that. Suppose that all I want to know from your code is whether it terminates or not without running it, okay? So you give me your code, and all I want to know is like, I'm feeling very generous. And so I want to, I want to say, okay, you're going to get full credit, CS135 or something, as long as you don't have an infinite loop and your program actually terminates, okay? You get full credit for that. Can I write a program that can check code and tell me if the program terminates or not? Can I do that? Question for the chat. Or basically tell it that it'll run forever or not. Yes. No. No, it would take forever. No. So I got one yes and a couple of no's. The no's have it, and that is correct. You cannot. Here's the thing. For a very specific input, such as something as simple as CS135 assignment, maybe I could do it. Maybe. I could. I mean, if they don't have any loops in their programs, then odds are it's going to terminate, right? So I could do it for that. But I am asking the big question of any program they write, will it terminate or not? Not just a specific subset of them. And the answer is, you cannot. Because you cannot test them all. Because you don't have infinite time, right? You cannot create them all. You can come up with all the possible examples, big, massive if statement in your code that just literally looks at the entire code and accepts it or not. Like machine learning or something. I'm just training it with old assignments. If I give the same assignment every semester and also missions I just gave them in there and I did machine learning on that, I could train it all I want, but it's still making a guess. And I cannot deterministically say, I created a program that I will 100% always guess correctly. And that kind of comes into the Church-Turing thesis and basically the greatest problem, the halting problem, and all these things. That, there are things that you cannot do with a computer because it cannot do them. And the reason why is because they're too hard to do. There's things such as undecidable problems, and there's things that you cannot do in finite time. And the halting problem being one of them. So, unfortunately, not to break your dreams, some things you can't just code a solution for. If you had infinite time, maybe you could do it, but you don't, right? And so, don't worry about that. Sap problem is a tiny subset of the greatest problem. We'll come back to that later. But yeah, so that was kind of my introduction into Turing, and I wanted to go into a tiny little aside as I was creating this at 3 in the morning, and it sounded interesting at the time. Who created the Turing Machine? And it turns out that it's Alan Turing, and he did it in 1936. And he's actually known by a couple of people as the father of computer science. So he's a big shot in computer science world. And look at the year, 1936, you're thinking like, what kind of computers are we talking about in that year, right? Like, that's pretty old stuff. You're right. The Imitation Game talks about that, and you should watch it. I know, like, Dr. Wally tells his automata class to watch that class, to watch that movie. It's pretty good. And it gives you a good sort of general overview of the situation at the time. And he actually used a Turing machine to crack Enigma, which was the encrypted messaging system that the Germans used in the U-boats. And that actually weakened U-boat communication because now they could see where they were, that Enigma code, and they could avoid the U-boats so that they didn't get sunk. And U-boats were one of the biggest threats for allies in World War II. And it actually allowed more supplies to arrive to England, which allowed D-Day to happen when it did on June 6th, which is a month from now. Of course, many, many years back in 1944. And frankly, he saved millions of lives. And why do I say that? Because suppose that he had not cracked the Enigma using the Turing machine. Suppose that the Enigma had remained uncracked for either another year or just never uncracked before the end of the war. Well, I went ahead and listed a couple of possible scenarios of that. Well, first of all, the U-boats would continue to dominate the Atlantic, so they would sink more boats, which would, as a result, delay D-Day by 1 to 2 years, which, as a result, means that Germany continues to send V-2 rockets to England. There's more Holocaust happening. They fortify France more for the impending invasion, which makes the invasion harder. And then BBC actually did some research on this, and they said that about anywhere from 14 to 21 more million would have died in those 1 or 2 years. And yeah, in the worst case scenario, actually, in 2 years, anything could have happened in terms of nuclear technology. Germany could have gotten a nuclear bomb, but even in the best case, the U.S. would have gotten the nuclear weapons, which would have meant they could have bombed Berlin just like they did with Japan to end the war. So we could have had a nuked out Germany, which would have, of course, caused more deaths. Whether how you feel about the bombing of Hiroshima and Nagasaki, that's off the chart. But that's frankly the best case scenario if they've gone and used nuclear weapons. In the worst case scenario, yes, Hitler makes nukes and then we have a Cold War, or we just have a nuclear war in general. So don't let anybody make fun of your profession. Computer science has been saving millions of lives since the 1930s. So, and look at today. Thanks to computer science, we're able to have class online. Thanks to all the technology, we can do this remote learning stuff. So I think this is our time where people in a couple of years will be like, oh, wow, okay. Technology has actually helped us. And who did that? Computer scientists, not computer engineering. Boo. So anyways, that's where I'll stop on that one, because you will all probably have to take, if you're a CS major, UNLV CS 456, which we'll talk more about automata and formal languages and Turing. And yeah, check out Turing. Check out The Imitation Game. That's a pretty good movie. But anyways, back to algorithms and in the follow-up of this class being 477. So okay, what makes an algorithm good? Okay, let's talk about that. There's a couple of things that I wrote down here that I think we could agree on make an algorithm pretty good. And that is, first of all, the most important one being that it works, right? But once we know that it actually works, we can move on to these kind of things, such as is it clear? Like, can somebody understand your algorithm and know what is happening so that we can know that it's correct and that it actually is a good solution? That's an important thing that a lot of people can kind of not think about when they're thinking about algorithms. They can, like, if you make an algorithm that's really good but it's extremely complex, no one's going to be able to implement it and no one's ever going to use it. So, there's a certain limitation on that. But unfortunately, for some things, all we have are complex algorithms. So I'm not saying that you have to have that, but it's pretty nice to have. You obviously want to have a well-defined, and this is, of course, if you're making an algorithm as well, a well-defined input and output. You want to know ahead of time what you're trying to do with this, what is your input going to look like, and what do you want your output to look like, okay? And then we actually move into the feasibility aspect of the thing. Can we get this done in finite time? Because otherwise, if you have this amazing sorting algorithm that is just called Bogosort, which just randomizes everything every time it runs and hopes that it actually sorted the thing, it's going to take forever to run. So I would say that it's an infeasible solution to your problem, because you could go and watch The Imitation Game a billion times and this thing would still be running, right? So I don't think Turing would want to use Bogosort to crack Enigma, So you want to have something that is finite in time, but more than that, that is actually fast. And the faster, the better. And with space, the same thing. You don't want to have an algorithm that, think of hashing, right? Perfect hashing. If we just had all the space in the universe, all our hashes could literally be perfect hashes, right? We could just convert it into a number that nothing is repeating and anything like that. Like phone numbers. You make the size of the entire phone book, and you're good to go, right? You could do perfect hashing, but of course there are limitations to that, and the less auxiliary space is going to be the better, unless you just have all the memory in the world. And finally, when you're creating an algorithm, this is something I wanted to just add in. That's why I got a little plus into it, because it's not really part of it. Make it language independent, and by that I'm saying, if you code an algorithm that is like dependent on how a programming language works, it's not a good algorithm, because your programming language may die in 20 years and the next cool thing will be out. You want it to be something in pseudocode or a theoretical explanation of something which can be applied to just any language that is Turing complete, basically, that is following the Turing machine. You don't want to have something that is so unique that only works in your environment, because then what's the use of that, and frankly. So from here on, before I go on, I'm going to ask you guys to list a couple of the algorithms that we learned in class. So what are some of the algorithms that we learned? Go ahead and just spam them out. Not data structures, algorithms. Bubble sort. All right, I'm going to put bubble sort because it was mentioned. I hope it wasn't the first time you saw bubbles are in this class. All right. DFS, BFS, breadth first search. That one is on the test tomorrow. Quick sort. Minimum spanning trees. Well, there's 2 of them. So I'm going to just go ahead and put prims. And then, of course, cross goals. What else? Dijkstra's. Yeah, Dijkstra's a big one. Dijkstra's. Shortest path. Quick sort, merge sort. Meme sort. Post-order traversal. Well, is that an algorithm? It is an algorithm in the fact, but I think more importantly, how to traverse trees maybe. But even, no, but see, that's too specific because that's more of like, I mean, it counts, but like, it's very, very, very peculiar to the situation that you're working with a tree. Like, okay, if I just tell you like, yo, here's some data, do some traversal on that. I mean, it's only useful if it's a tree, right? So I'll put it in, but like, you know, the same argument could be said about depth first search and breadth first search. So why not? All right, heaps. So heapify is an algorithm, but it's not. But again, it's more related to a data structure. I think a better usage of that is heap sort or a priority queue. They're different. They're both working with a queue, but see, that's something that's actually useful. Like you can use it in assignment 12 if you were doing that with the ent list, right? You have a purpose for that. Heapifying is a means to an end. It's a means of doing heap sort or making a priority queue. But those are the actual algorithms that are useful to people out there. No one's gonna in the real world be like, yo, heapify that. It's like, what do you want to heapify that? Are you building a priority queue or are you doing heap sort? You know, those are the ones that you want to think about. Yeah, I don't know what genome. Insertion sort, topological sort. I mean, a better question is, what are you trying to do with topological sort? And that would be actually more of the algorithm. Genome sort was in 2018. Oh, really? I don't know. It's been a while since I thought it was actually a meme. I don't know if this was a real thing. Okay, I'll put in one more of the ones that you guys talked about. And yes, pre, post, and in order are sort of, depth first search, at least in the sense that you're going deep into the thing and then you're printing in a certain order. So yes, they're all essentially some sort of DFS or BFS, like level order is BFS, breadth first search. BOGO sort, all right. Lamp sort is basically quick sort, but it would be an injustice to say that we talked about it because I didn't tell you that much about it, so I don't want to give fake news to the people who are watching this who never took the class or something. So okay. Anyways, enough. We have more than enough. I was hoping to get 2 more, but that's okay. I don't even know if we did more than that. So okay. All right. So we got a couple of things here. I did mention the tim sort is what Python uses, and you guys know tim sort if you know merge sort and I think selection sort because it's what it uses it, right? So these are some algorithms that we learned in class. Now, why am I listing them here? Well, I'm going to ask you, are some of them similar? Like, how are they related? And I put an example of, we're getting some lag. Okay, we're back. Yeah, I want to ask you, are some of them related? And here's an example of one of the obvious ones. Prim's minimum spanning trees and Dijkstra's are related in the sense that you're basically doing the same algorithm minus that tiny tweak where you're adding the weights instead of just replacing them, right? I did teach you, Kawa, I did teach you bucket sort. And in your class, we actually also talked about radix sort and Huffman's code and a bunch of other ones. But that's because that was a smart class. We went faster than this class. we even have someone present about red-black trees, which we didn't talk about. So, but yes, we did talk about a couple of other algorithms in that class. So just different things that we teach this class. I don't think we talked about tries that semester, whereas this semester I had a video on it. So yes, GGs. Okay, so are some of them similar and how? Here's an example. Nah, you guys were not dumb. You're probably one of the smartest, if not the smartest, 302 class that I've ever had as a whole, not as individuals. I told you guys you were smart. You guys are smart. It's just that, you know, we did less than the other class. I think it's because I had to do 3 classes at once. And so even though one class was going faster, one of them slowed us down and vice versa. So we were held back by a class. Whereas when I did Kawa's class, I was teaching just one section. So if we did things faster, we just kept going fast and furious. And there was no class after us. So we could just keep going and on. Ooh, I'm getting lag. Are we good? It's kind of lagging. Okay, we're back. It's green now. Nobody's doing the hydrate thing. Anyways, let's bring it back together. All right? So tell me, what are some of the similar algorithms that we talked about? Like, how are they similar? So prim and minimum spanning, prim and Dijkstra's are pretty similar. You can see that. Give me other ones that are similar. Okay? Breadth first search and DFS, queues and queues. Oh, we never talked about queues and stack, by the way, here. I think that's why I had 2 more things. But then again, queue and stack are, I would say stack is not really an algorithm. A queue is, though. Not even, actually. I don't know. Maybe not. I don't know. I wouldn't put it there, actually. Okay, so insertion and selection sort, they're both stable. I mean, that's the feature they have, but that doesn't make them very similar. BFS and level order, okay, I could kind of see that. BFS and level order. Lamp sort and quick sort, I mean, are similar only in the sense that one is iterative, one's recursive. I think you guys are not. You're thinking like you're not thinking outside the picture. Okay, let's kind of think outside the picture for a second. Okay, for example, let's think about sorting. Okay, how does merge sort work? Okay, merge sort divides things in half, and then divides it in half again, and then divides it in half again. So it is dividing into a smaller problem and then bringing it back together. Okay? Now think about quicksort. Quicksort is also, in a way, dividing things in half, almost half. I mean, partitioning things based on whether they're smaller or greater than. And yet again, you know, it is dividing the problem into a smaller subset of problems. Okay? So that's more of what I'm talking about. The logic behind quicksort and merge sort is not that far different. You're dividing and conquering things. Same with binary search, actually. You're right. With binary search, you're dividing the problem into smaller subsets by cutting the list in half, and then the half again, and then the half again, and the pen, and basically the solving your problem. So that's more of what I'm talking about. There are certain types of problems that you can solve by dividing them into smaller steps. There's other things such as greedy stuff, like, for example, all the traversals and depth first search and post order, they're related, they're similar, but oh, hold on a second. We have someone who's doing some shady things. I don't know. Someone's trying to do weird things in chat. Anyways. But okay. So someone was trying to curse in chat so that it could appear on the lecture, I guess. So I'm trying to see if I can kick them out of the lecture. But anyways. That's fine. If something gets away, then whatever. We're all adults here, so big deal. Okay, but anyways, okay. So, for example, we got depth first search and all the traversals, and the way that works is you got a tree or you got a graph, and then you're trying to go as deep as possible to print as much things as you can, and when you run out of places to go, you back out and you find other things, right? These are called greedy algorithms. The other option is, for example, to to go into something like binary search, actually. Binary search, again, you keep splitting it half and half and half, and there's no sort of intelligence to what you're doing. I mean, it's a smart algorithm, don't get me wrong, but there's no intelligence to what you're doing in the sense that you're just going as deep as possible when you're trying to figure out a problem. So there's a lot of algorithms that share some basic concepts in common. And now that it's the end of the semester, I want to bring it together by talking about what those techniques are. So let me just go right into them. So algorithm design techniques. And there's 5 of them that are pretty predominant per se, of which we mostly work with 4 of them. And I'll show you the 5th one, but you know, we didn't quite see it. Ooh, we're getting lag. Is that, can anybody hear me, or did it die out? For those of you on YouTube, stand by. We're trying to get these people back online. Yes. I think we're coming back. I think we're coming back. I can see it kind of wanting to come back. Yay, we're back, guys. We're back. Okay. It's okay. So I don't know what happened, but it's still lagging a little bit. So we'll give it another second for it to kind of revive itself. Okay? So hello there, everybody. It's back online. I'm gonna post on Discord. Let me check and see how bad we're doing on the delay. I think it's dead again. Can you guys still hear me, or is it gone again? All right, hang in there, guys. We'll just wait. I'm going to try to restart the stream. I'm still recording. Stopping stream. Dang. Even that is taking a little bit. I have a feeling it's OBS related too. I'm restarting stream. Even my ads are freezing. That's how you know it's really bad. Alright, I'm gonna start going up again now. Start streaming. Oh, it'll be in the exam. You don't even know. It will be. Okay. We'll just wait and hope for the best here. Let's go back to the other chat in the meantime. Main background. I'm getting 55 kilobits per second upload. And now it's 0. And now it's 150. So it's definitely struggling. But the download speed is fine. So I guess it must be Cox throttling me. I'm not going to lie. I'm actually about 200 megabytes per second download. I'm going to see what the upload says. Oh yeah, my upload is like, it's not even loading. Oh, it kind of wanted to for a second there. You know, if we could have survived one more day with the internet, we wouldn't have had this problem. We'll just wait a few minutes. So if you're watching this on YouTube, then you can just fast forward until the iPad is back on. Oh, I see it green. I see it green. Are we back online? I think we're about to come back online. I think it's coming back to life. Oh no, we're red again. It's like it wanted to, but it didn't. We'll just wait. I see you. That's a good sign. But wait a second. Make sure everything is up and running. Refresh now. Are we back this time for good? I can see it kind of going down, like it wants to go down. Like I can see the. I wish I could have a little corner here where you could see the bit rate as I'm doing the stream, so then you can kind of see what's happening. But I think we're good. Yeah, I think we're in business now. The weird thing is, my download speed is fine. Like I actually checked that I had 200 megabytes per second, which even though I have Gigablast, 200 megabytes is better than what I was getting like 2 weeks ago or a month ago, right? When I was getting like 1 megabit per second. But the upload, which has been relatively stable, that just died out. It was like at 0.001%, or sorry, 0.001 megabit per second. So I had some internet to the point where I could see your messages and I could send messages on Discord. But I couldn't I guess I couldn't stream. I am broadcasting audio, so if you have audio problems, just refresh. Yeah, refresh. Okay, we're gonna try to keep going now. So if you're watching on YouTube, I guess now we're back. So how many people do we got? I think we got 29 viewers. Okay, we're gonna try to carry on now. 40 viewers. 555K is anyways high for 720p. Yeah, so either way, I don't know. It should be good, but it's not. So okay, all right. Back to the world here, guys. We were talking about algorithm design techniques, and I was going to introduce you to basically the ones that we've been doing this semester. Okay, so let's jump right in, so we can catch up on some of the lost time. So we can, hopefully the internet holds them longer for like 1 more hour, and then they can die for like a month, and I'm okay. So just 1 more hour. Okay. So the algorithm, we were looking at the comparison between like how are they related and things like that. And it turns out that all the algorithms that I taught you this semester can be sort of brought back into talking about these 5 main points, 4 of them actually. And so the first one is called a greedy algorithm. And actually, let me name them all, and then I'll talk about them. So we got greedy algorithms, we have dynamic programming algorithms, divide and conquer, backtracking, and randomize. And there's also heuristics, but we'll get to that. All right, randomized algorithms we didn't really talk about, but as you see, I'll give you an example. Okay, the ones that we mostly have done, and actually the one that you're probably most familiar with, is going to be the greedy and divide and conquer. Greedy algorithms are those where you're basically most of them are actually not that efficient, so they're inefficiency, at its finest, I suppose, but they get the job done. And in that sense, you can say that usually they're algorithms that, when given a choice within the program, they don't care which choice they make. They just make one and they go as far as they can before they can't go any further. Examples of that: merge sort, you could say, is a greedy algorithm because it just splits the data until it cannot anymore and then merge the data. It doesn't discriminate how it splits the data. Depth first search and all those traversals, they keep going as far as they can and then they stop and then they go back and do other parts, okay? The going back part is actually going to be the backtracking. But yeah, all the, like, if we go back to this list, is bubble sort greedy? In a way, because the algorithm basically just keeps bubbling things nonstop until it gets done. So yeah, I could say bubble sort is in a way greedy. Depth first search is definitely a greedy algorithm. Breadth first search and traversals in general are usually greedy of the nature. But I would say depth first search is definitely one of the best examples of a greedy algorithm. Okay. On the other hand, when it comes to prim and Kruskal's minimum spanning trees, I'd say Kruskal is a bit of a greedy algorithm because you just sort things out and then you're picking edges as they come. You don't care how they go. On the other hand, Prim is a little bit more elegant than it being a greedy algorithm. So we'll come back to that one. Heap sort, is that greedy? I would say Heapify and all of those parts of heap sort are pretty greedy because they work on a small subset and they just keep going, fixing the tree as they go. There's no elegance to them in that sense, okay? And so most of the algorithms that you were going to find, because they're easy to implement and things like that, are greedy algorithms. And usually in the test, for example, breadth first search or depth first search, when I'm like, yo, I need you to start with this letter and go, and whenever you have a choice, pick alphabetically one of them. The fact that I had to tell you that is a sign that it's a greedy algorithm because it just picks whatever it can go and keeps going. And of course, because you can pick whatever you want, you can have a lot of answers for that and it makes it harder to grade, right? So that's kind of a hint of it being a greedy algorithm. All right, moving on. Let's talk about divide and conquer first, actually. Divide and conquer algorithms, by the way, it doesn't mean that an algorithm has to be specific, always just one type of this. It can be a combination, and it usually is. As I was talking about greedy algorithms, a lot of them are divide and conquer. Divide and conquer is probably the first kind of algorithm example that you learn in 135 back in the day. And that is taking, in general, and this is not just for programming, but in life in general, you take a big problem and you divide it into smaller subsets of problems, right? If I tell you, code CSGO, if you just try to code it and not like just start to end, not a single test, you just code, you're gonna have a really hard time. What do? You divide it into smaller problems, you work on those problems, you solve those problems, you debug them, you get them working good, and then you work on other problems, and then you put it back together. For example, with the assignment, you maybe work on printing out the map. Then you're working on maybe moving in the map. Then you work on shooting in the map. Then you work on the AI. Then you work on, I think that's it, pretty much. I mean, moving, shooting, rendering, I suppose. Other tiny little bits, right? Then when you put them together, you got to connect everything together, right? But you don't need to be working on the AI when you're just coding how to render the map, right? They're pretty separate in that sense. And so a lot of the algorithms kind of work in the same way. For example, back to merge sort. Merge sort works by splitting a big list into tiny lists until it gets to 2 individual members that it can easily sort because it just picks the biggest one or the smallest one depending on what you're doing, right? That's divide and conquer at its finest. What are other examples of divide and conquer? Anything when you're dealing with heaps, heap sort and that kind of thing, you have I don't have to do hand gestures. I have a piece of thing here. You heapify this, and you heapify the bigger one. You make that Triforce that I was talking about. You build the thing from a smaller problem to bigger things, right? You divide the problem into smaller subsets. And even within the heap sort algorithm, it's divided into like heapifying part, then removing the minimum key, and so on, right? So divide and conquer, very popular because it's also something that is easier as a human to deal with. You deal with smaller problems instead of trying to solve everything at once. So lots of algorithms that have that technique or mantra. There's a better word that I'm thinking of, but it's like on the tip of my tongue. Okay, let's talk about some of the fancier ones. Is binary search divide and conquer? Absolutely. Binary search is super greedy, and it's divide and conquer too. For many reasons why. One of them is, of course, splitting. See, there's two sort of mentalities to divide and conquer. On one side, divide and conquer is dividing a problem into smaller problems that you can fix. The other side of it is simply dividing into a smaller problem of itself. That's another format of divide and conquer. So I would say divide and conquer can really be thought about as two different things. One of them being take a problem and split it into different small pieces that are working together to solve the problem, such as heap sort, such as heap sort because it has heapify and then delete min key. And then the other part of that being divide and conquer in the sense of like splitting a list into smaller lists that you can then more easily solve. So it's two things in one really when I'm talking about that divide and conquer. Would all recursive algorithms be considered divide and conquer algorithms? I don't like saying the word all because it's dangerous, but I'm going to tentatively say yes. At least I can't think of one that is not. Because when you're recursing over something, you're trying to get it to a base case. You're slowly working on the problem until it becomes really small. So I would say that, yes, I would say that that's one of the two mentalities of divide and conquer where you're splitting into a smaller problem. Again, one mentality, splitting into smaller problem. Other mentality, which is also divide and conquer, splitting into different independent problems of itself, such as assignment 12 and doing things like doing this and doing that and doing this and so on. Okay? Strasson's algorithm, I'm not sure. I don't remember Strasson's algorithm, to be honest with you. So I would lie to you if I said like, yeah, sure, of course not. So whatever. But there are different ways of multiplying a matrix, and so a lot of math problems can be applied with divide and conquer solutions. So I wouldn't be surprised. Okay, let's talk about dynamic programming. This is a really fancy one. This one scares a lot of people. They think of dynamic programming and they think it's like some big brain thing. And I'm not gonna lie, most of those algorithms are a little bit trickier. They're not as intuitive as a greedy algorithm. And that's because when we think of something, we're usually thinking of a greedy algorithm to solve a problem or a divide and conquer to solve a problem. We don't usually think as in a dynamic programming sense when we're trying to solve something. Modular programming, yeah, in a way, because you're splitting it into smaller modules, which are smaller problems. So sure, you can go with that. But anyways, dynamic programming. So with dynamic programming, the idea is, and we've seen it, we saw it a couple of times, and I already even talked about dynamic programming in person, if you remember when I was talking about Fibonacci and Python. And so dynamic programming is the idea that when you solve a piece of the problem, you remember what you solved so you never solve it again. Okay? So the example where you heard dynamic programming before was with Fibonacci. With Fibonacci, if we're trying to solve the fifth number in Fibonacci, over factorial or things like that, you don't want to recursively solve the fourth, the third, the second, the first, and hit the base case, and then do that all over again. And then if you want to solve the sixth number, recompute every single one. You don't want to do that. You want to remember the previous values that you've already computed so that if you ever need them again, you can use them and speed up future computations, right? So if you start from scratch and you got to compute the sixth number, yes, you're going to have to go 6, 5, 4, 3, 2, 1. But if later on I ask you what the seventh number is, you don't want to recompute 7, 6, 5, 4, 3, 2, 1. You want to remember that you've already computed the sixth one, use that value, and then apply it to solve the seventh value. So the idea of remembering previous work is the heart of dynamic programming. And we've actually done a couple of algorithms now that involve dynamic programming. The best one being Dijkstra's shortest path. Dijkstra's shortest path, we are computing the paths as we go, and we keep a table of them of what the best path is. And next time that we compute a path, we take the previous value that we already computed for a certain vertex. So like, for example, suppose that we got this graph, right? And well, to make it more interesting, maybe we go ahead and do that. Okay, so we go ahead and we compute from here to here. It takes let me put some numbers to make, I wanted this example to make good sense here. Like that, okay? So with Dijkstra's, we go ahead and we compute that, and then, I don't know, this don't really matter, let's just do 10, 10, okay? We start at 3, we compute this node right here, and then from here, we can go ahead and compute this edge, and then that's it, and then we move on to compute maybe this edge right here, and then from there, we go in and compute this edge right here, and then, technically, as we computed this edge here, we said that the fastest path was 5, right? So, and then when we go ahead and we compute over here, we go ahead and we update it and say that the fastest one is 4, okay? So, here's the thing. When we're computing, for example, this vertex or this vertex, we don't compute back from scratch. We remember how long it took us to get, for example, so if we're trying to compute like this edge right here that I'm highlighting, we got to remember how long it took us to get here, right? It took us 3 to get there. We remember that because we have our little table that we do. If we had to recompute it again from start, like if we perform something like depth first search or breadth first search, every single time we visited a node, which you could do shortest path like that, it's just very inefficient. And that's the reason why, because every time you're recomputing things that you already knew. But because we keep that in the table and then we update it only if it's smaller, that's the idea of remembering what we've worked so far so we don't repeat our computations for no reason. It's a little bit different than Prim, but Dijkstra, the fact that you're remembering that is what really makes it dynamic programming. So it's using your older solution to produce new ones. Yes, pretty much. You could say that. It's using older ones to remember new ones. Now, of course, because of that, it's sometimes it's a little bit trickier than that, because how do you remember old solutions is not always easy. In 477, they'll talk about Liebenstein's edit distance and Jaccard's and all of those. And Liebenstein, you can also do with dynamic programming. And what that means is, like, if I have the word cat and the word dog and the word mat, I ask you, what's the difference between cat and mat? You can tell me that I changed the C to an M, and I would consider this to be an edit distance of 1. Over here, though, I have to substitute C for a D, A for an O, and T for a G, so that's an edit distance of 3, right? But here's the thing. If I ask you what the edit distance is of the word cats and dogs, you can use this knowledge, apply it to that, and the difference being actually so 3, right? Because the S is the same. So you can use that knowledge of the difference between cat and dog and apply it to cats and dogs and use it to compute the distance. And even if this wasn't like as trivial as that, if it was like, instead of dog, it was like doggy, in that case, you can still use the fact that this is an edit distance of 3, and then you can add in the fact that this is +1, and then here's another +1. With edit distance, the 3 things you can do is insert, delete, and substitute. So basically, you use the memory of previously figuring out the difference between cat and dog and apply it to things like cats and doggy. So most of the really nice algorithms, but also some of the trickier ones to learn, usually use a form of dynamic programming to the point that some languages like Python apply it so that if you call a function on Python that takes a certain input and produces a certain output, and you call it more than once, Python can actually remember that you called it and keep track of that, so you don't have to do it as a programmer. And so like you can code Fibonacci in a recursive way in Python, but it'll actually remember things. So the next time you call it, even though it's recursive, it's not even going to do recursion. It's just going to keep a list of records of what like input and outputs was for there. Of course, you can't have side effects at that point in your functions where they affect outside variables, otherwise things break. But as long as that is not violated, then and the function is really self-contained, then there's nothing wrong with remembering, right? Python is smart in doing that. That's called memoization, and like I said, we talked about it at some point. So anyways, that's dynamic programming for you. Moving on, backtracking. Backtracking is like when I make a mistake in an algorithm and I'm like, and then back out, basically. That's kind of what it is, actually. So backtracking, have you seen it? Do you know what it is? Let me think about it. I don't want to tell you for a second. Does anybody think of an example algorithm where we've done backtracking? Can anybody think of one? And that way it tells me whether the stream is still up. We got 53 viewers. That's pretty nice. Heapify. Heapify. ABL. Depth first search and inception. I like that one because that's the one that I was expecting most people to say. Depth first search and inception. The other ones I got to think for a second. ABL. Not really. You don't backtrack in ABL because otherwise you probably screwed up. So let's talk about depth first search, okay? Depth first search is the perfect example of, well, first of all, did you say depth first search because it was literally written there? Because otherwise, I'm going to yell at you, Sam. Like, what the hell? It's literally written there. But I hope, you said the word inception, though, so I guess that's better. But, yeah, okay. So depth first search is a really good example because, I feel better now. Because when you go as deep as you can in a graph, so, here I am, like, going super deep here. So, like, let me draw a graph. So, here's a graph. And I'm doing depth first search. I go as far as I can here, and then I backtrack to the last place where I had a choice, and then go there, and now I'm done. Okay? That is depth first search. And so the idea of backtracking, so you don't start all the way from the beginning, so you don't start all the way from here and then do a choice again, you save some time by doing that. That is backtracking. You sort of backtrack when you're doing a traversal also in post and pre-order because, again, they're all depth first search in a way. Now let's think about ABL. Why is ABL not really backtracking? Because with ABL, it was one of you that with the test corrections where I told you like because you did some weird thing where like you had to fix the child notes when you changed the parent because you did a double rotation when you should have done a single one. Here's the thing with ABLs, as long as you do the right rotation, you never have to worry about fixing the children edge heights. They will be okay. You only go upwards. So I wouldn't say that's really backtracking. Heapify is a good example. And is it? Yes, kind of, because like when you're more than heapify, when you delete a min key, you gotta fix the tree back of what you did, right? You gotta fix because you swap it with the last element in the list, and then from there you have to sort of bubble it back down. I could say that's kind of backtracking in a sort of best sense, but a good example of backtracking is in general recursive algorithms, because when the recursion goes as deep as it can, it usually comes back out of the recursion until it can go anywhere else. And so greedy algorithms and backtracking algorithms share hand in hand a lot. One of the examples that I sometimes give for backtracking is building the tree at the end for a minimum spanning tree, or doing the shortest path in Dijkstra, following the parents. I could say that is an arguable example of backtracking because you're sort of backtracking your path. But I'd say it's a little bit misleading because I like to think more of backtracking of saving time starting from scratch. And that's more of like leaving a trail of crumbs. So a lot of these techniques are so shared hand in hand that I would say that it's kind of hard not to prove that something is definitely not one of them, because they all have a little bit of each. But yeah, anytime you use recursion, it's probably going to be backtracking. Just like anytime you do something rather simple, more than likely it's going to be greedy. And if you're keeping track of like values as you're doing it, it's probably going to be dynamic. And then if you're splitting a problem, it's going to be divide and conquer. So it's all really shared. So anyways, I'll move on from now. Randomized algorithms is the only one that I don't think we really talked about it. Only very briefly. I might have mentioned it in any of the sections that like with quicksort. So randomized algorithms is a lot of the times picking what to do next is time consuming if you want to do it right. And so, for example, in quicksort, picking the pivot, the ideal, the mean, the dream is to pick the median as the pivot, because that median value would give you the perfectly balanced left and right as all things should be. Unfortunately, finding the median is a very complicated problem in terms of time. And if we find it, it means we have to look at the entire list, at which point we're hitting O squared anyways. So what do? We just went ahead and said like, yeah, we're gonna pick the biggest value of the list by saying like the biggest index or the smallest index, right? That's what we do, right? Call it a day. Well, another way that you could do it is you could randomly pick one. Just literally not saying always pick the last one, always the first one, which in a way is kind of random because of the way the algorithm works. But I'm saying like literally pick a random index and then move it to the end and then do your quicksort. That RNG actually helps efficiency because you hope that RNG allows you to sort of be happy with probability that you're picking something really random. And so, no, stream is not dead. Refresh. I'm getting green lines all over right now. So, yeah. So really, the only really time that you may have seen randomized algorithms this semester was with quicksort, with the RNG to pick as a pivot, which may improve the space complexity. Now, somebody did say for assignment, then we have to generate random types of the alpha, drone, omega. Is that randomized algorithm? It is not, because you did that just to mimic something that we're trying to work with. But it's not really part of a solution to a problem. Randomized part of an algorithm is, for example, maybe picking which letter you want to start with when you're doing an algorithm. That could be arguable for a randomized algorithm. Like picking which letter to visit next if you have given a choice in that first search. I could argue as a randomized thing, but the only time you really want to do randomizing things is when you don't affect your quality of your algorithms, like you still want it to be 100% correct, but also it actually helps the time complexity or space complexity of the problem. So Bungo sort, I suppose, is randomized, but it's crap. So like, why would you do it anyways? So randomized in the sense that it actually helps your problem and not just like doing it for the lulz. Okay? All right. The last one that we didn't really talk about either, and it's not really much of a technique as it is more of like a way of doing some things because you have to do it, is heuristics. Heuristics is an educated guess. And that is for problems where really, and that kind of goes into the question, why would I ever make an educated guess instead of accurately solving a problem? Like, for example, it's like me saying, I'm going to go ahead and solve Dijkstra, but at some choices, instead of actually picking the smallest weight, I'm just gonna go with what I feel and make an educated guess. And so, no, hard coding is not heuristics. And so, making an educated guess is basically is done because you want to speed things up. And sometimes, as we'll get in a second, there are things that you can't do really fast. And heuristics is really the only choice if you want to get a problem done before you die or the universe expires. And so we'll get to that in a second, but just think of heuristics as an educated guess. A really good example of that we didn't get to talk about is A-star. And so I'm going to give you the 5-second summary of what A-star is. A-star is Dijkstra, but with an added layer of complexity where you make an educated guess that is in the direction of your objective. And you can actually implement A-star for assignment 12. And that's why A-star is used a lot in gaming and pathfinding and things like that. Because what you do is this. When you're picking which edge to check next, you don't and suppose that there, you have different options, and you usually pick the one with the lowest weight, right? Okay, now you don't just decide based on the weight. You add a heuristic value, which you randomly assign based on a heuristic. So not randomly, you assign it based on a heuristic, and then you're going to use that in comparison to the possible weights, and that heuristic is going to bias things. So maybe the heuristic is really high for a certain vertex, and even though it's not the lowest weight available that you could pick, because the heuristic is so high, you're going to go with that one, because that's what you got your hunch going for. So what's a good heuristic to do for pathfinding? Well, if you're trying to do Dijkstra for Google Maps, you don't want to have to build the entire graph of the Earth. More than likely, you only need to go, if given a choice of where to go, you want to go in the direction of your objective. And if you know you got to go north, then you can build the graph on the north part of like the north part of the map. You don't really have to worry too much about the south part. You give a priority to the north because more than likely, you're going to get closer to your objective. And so that's what A-star is all about. A-star is about having a heuristic that is sort of giving it a direction to where your goal is and sort of biasing it. So if I have a map here, assignment 12, this is my grid, and here's the bomb, and here's my player. Or maybe not there, but like here. Okay? I would want to check this layer right here. But the next layer that I can check in terms of distance would be this entire layer. But instead I say, no. Let me focus on checking this side because it actually gets me closer to the objective. And there's going to be a limitation to that where I still want to keep checking here, but I'm biasing myself to go this way. Okay? And so that's what A-star is in the short version of that. Hopefully they covered in 477 for you. It's not really part of 302 anyway, so I don't feel bad about not showing it. So anyways, this leads me into the PNP stuff, which is the cool stuff, right? Because why would I ever do heuristics on something like this? To save time, and not just that, because sometimes it's all I have. So what is PNP? PNP is the idea of taking all of the problems that we have in CS, not in our lives. Well, I guess you could say some of our problems can be considered in P versus NP, and separate them into categories depending on how difficult they are. And so the most common category of the problems that we've been solving in 302 with the certain algorithms that have been solving them are going to be the P algorithms, P problems. So P problems are basically 302 problems like Dijkstra, sorting, pretty much anything that we've seen, actually. I don't think we've seen anything that's not P, because otherwise you'd be running your solution for quite a long time. And so what are P problems? If you think back to what I was talking about, the Turing Machine, P, as I say here, is a set of problems that can be solved by a deterministic, finite Turing, well, finite I suppose, Turing machine in a polynomial time. Okay? Polynomial means, if you think of time complexity, O of n to some power. So n to the 5th, n to the 6th, but that power is defined. It's not just like n to the n or something, okay? Otherwise, that's exponential. If it's defined, so for example, if it takes us n squared to do bubble sort, or n log n to do quick sort, or Dijkstra, or for example, I think that's what was v squared, and then for prim or Kruskal's, e log v or v log v, whatever it is, all of those are defined because there's something. They're not exponential. They're n squared, n cubed, log n, n times whatever, but still they're constrained within polynomial time. There are other problems that we really talked about that are much harder than that, and those are the NP problems. NP problems are basically, it stands for non-deterministic Turing machine polynomial time. A lot of the times people incorrectly abbreviate it to a non-polynomial time algorithm, although incorrectly, but still gets the point across. So non-NP problems, non-deterministic Turing machine polynomial time problems, are going to be problems that you cannot solve in P time, in polynomial time. When I say P time, I'm talking about polynomial time. What is an example of that? I'll get that to in a second. Let me first finish showing you the different options. I'm saying that like somebody asked it, but it came to my head. But really, they're problems that are going to take an exponential time to solve, or they just cannot be solved. Like, for example, NP problem is, when are they going to fix my internet? That is definitely on the NP quality, because that is not something they're fixing in my lifetime, probably. So, yeah. Okay, so first of all, P is a subset of P. Not true. P is a subset of NP. There we go. That's much better. What is the difference between deterministic and non-deterministic Turing machine? I could get into that, but that would take a while to explain. That's Google NFA versus DFA and things like that. And take 456, and then you will know the full story between those. Basically, whether you can go into a state when you choose to, or you can just, like, if you had that little state machine that I drew, notice how I went from like one state to another one. I can also choose not to go anywhere, and that kind of jumps into it. So yeah, P is also a subset of NP, okay? And yes, P is a subset of P, just like I'm a subset of myself. But anyways, what I meant to say is P is a subset of NP. And so anyways, so these NP problems can be discussed further by talking about NP complete problems, which are the ones that we're mostly interested. So those are going to be the hardest problems in the NP category or set. And here's kind of the interesting thing about them. You can't solve them in polynomial time, so you cannot come up with an algorithm that you can do in n squared or nq time. And I do have an asterisk there for a big reason that I'll talk about. But here's the catch. Even though you cannot solve them in p time, you can verify a solution in p time. So like test time. You got a problem in the test. You can't figure it out. But then you shouldn't do this, because I will find you and I will fail you for the class. You ask your friend what the answer to that question is, and he tells you that. And even though you don't know the algorithm, you can plug in your friend's answer and then see if it works as a solution to the problem. And if it does, you're good to go. So here's an example of a problem that you couldn't figure out in the time of the test, but given the answer, you can verify if that answer is correct or not by just plugging it in. And so that's basically NP complete problems. They're hard, they can't be solved quickly, but you can check the answer if you find one very quickly. And so that jumps into our heuristics. I can come up with a heuristic that can solve something in p time, but it's a heuristic. It's an educated guess, which means it's not even made. It is not for sure going to be correct 100% of the time. It might be 99.9% of the time correct, but there's going to be asymptotically at least one case where it's going to be wrong. And because of that, it's a heuristic. So I take that value, and if I really, really, really want to check if it's a good value, I can plug it into the problem, and I can verify if it's good or not. So then you ask, okay, well then why don't I just combine the heuristic and the plugging in and make the solution in p time? Because, as I said, the heuristic may be wrong. And if it's wrong, and I plug in the wrong answer, and I see it's wrong, I'm stuck now. I can't just like ask it for another one. The algorithm is going to always give me that one guess. So it's not like every time I ask it, it'll give me different guesses, and then I just, I'll check 2 or 3 times, and then I'll be good to go. No, that's not the way the force works. Okay? So those are going to be NP complete problems. Finally, we have NP hard problems. These are kind of the nasty ones. These are definitely the hardest problems per se, in the sense that they're at least as hard as the NP complete problems. They're definitely not solvable in p time, and they may or may not be verifiable in p time. So whereas these guys, if I have the answer, I can check it if it's good or not quickly. These ones, maybe not. And so here's a graph of what those look like as a sort of relation between each other. First, we have the P, which are 0-2 algorithms like Dijkstra's. From there, we have the bigger circle, which is the NP problems. And then that is the NP complete problems, which is that subset up here, like the Knapsack problem, which I'll talk about. And then you got your NP hard problems, like the halting problem, the graded problem that I was talking about. The NP problems are usually just decision problems, but NP hard can be decision or anything else, really. And anything that is in this class can be sort of reduced to a decision problem in a way. So don't get kind of confused with the word decision there. It doesn't have to be what you think it has to be. The thing you should ask, though, is the way I have this described, NP complete is a part of NP, and P it's part of NP. But is there such a problem that is not part of P and not part of NP complete, but it's part of NP itself? So like basically what the purple circle here is. And we're not sure, but if they do exist, we would call them, I guess they decided already, NP intermediate problems, which is the Ladner's theorem, which actually says that if such theory exists, there's like an infinite number of difficulties, like from P to NP complete, like P harder, P hardest, P even harder, P like cancer hard, and so on. So if there is different tiers, then there's tons of them, like infinite amount of them. Or there's none. We don't know. And so here's the thing. I keep saying we don't know. Yeah, cancer hard versus like extra cancer hard or something like that. So coronavirus hard, who knows? So here's the thing. I keep saying the word like maybe, why, blah, 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 because I asked you this question. Are P and NP the same thing? Like, are, P algorithms are the ones that we can do like in N squared or N cubed or whatever, right? NP complete problems, on the other hand, are problems that you can't do in polynomial time. But here's the thing. Just the fact that we have NP complete problems, is it just because we haven't found a solution that we can do in polynomial time? If I went ahead and asked you before you took this class, what is the shortest path problem? And you came up with this algorithm that is just cancer, and it takes like infinite time to do, but it can do it. And then I told you, oh yeah, there's dynamic programming and there's Dijkstra. Then you would tell me like, oh my gosh, this is amazing, and now I figure out that there's problems that you can do. Well, the same thing applies here in the bigger picture. We don't know for sure if the NP complete problems are just problems that we haven't figured out yet how to do faster, or if they're really a different kind of problem. And so that brings the question of, is P equal to NP or not? And I saw people say yes, but you can check. The answer is we don't know. Like legit, I wish I had an answer for you, but I don't. And that's because there is no consensus or proof whether P and NP are equal or not. What we do know is that whether or not they're equal, NP hard problems are still not solvable in P time. Dog is trolling. Go away, dog. Not right now. So anyways. So I have a reminder here to show you some common misconceptions in Wikipedia. I guess I can do that really, really fast. But first, yeah, I'll do that. Because I think it'll clarify some things. So I have it open here. I do recommend you check out Wikipedia for P versus NP. And where are they? Common misconceptions. Yes. Okay, so I'm going to read some of these out loud, and I'll post the link so you guys can check them out too. But here's the thing. If P is equal to NP, then that means that we have a solution for them, right? And that means a couple of more things, but I don't want to jump into that too fast. So I want to go one step at a time. Still, however, there's NP hard are their own category, and only some of those are NP complete. So even if they're equal, we still got problems like the halting problem, which we wouldn't be able to solve anyways. And I'm hesitant to say that even if P and NP was equal, we could still prove that NP hard is just its own thing. So we don't really just know. I mean, CS is a young field in a way. And by the way, $1 million for people who can figure this out. I don't know. I don't remember what the organization is, but they have offered a bounty of $1 million if you can solve whether P is equal to NP. And tons of people have tried. Some of them famous. Some of them became famous because they tried, and then of course they figured out that the proof was wrong, and they got laughed at, and then they disappear. But sometimes it's been in like the news and things like that. So here's a couple of common misconceptions of P versus NP, which I think will help us better understand. Yes, they are going to be in the exam. Yes. You can bet you there's going to be some P and NP stuff in there. Actually, I like the question that I did for that. So, NP complete problems are the most difficult known problems. That's a misconception. Because NP complete problems are not. NP hard problems are much, much harder. NP complete problems just means that the problem is exponential time to solve. It doesn't mean that they're that hard in the sense of hard. I'm going to show you a problem that is NP complete that is actually not that hard. Is the question to prove P equals NP? Maybe, maybe not. You'll have to find out tomorrow in 12 hours or 24 hours. Other misconception. NP-complete problems are difficult because there are so many different solutions. On the one hand, there are many problems that have a solution space just as large, but they can be solved in a polynomial time. So for example, minimum spanning trees. Minimum spanning trees have tons of solutions, potentially. You know, you saw that there can be more than one solution. By the way, you should note that the test tomorrow. Whereas like some problems just give you one clean solution to something, right? And so like Dijkstra will just, you know, give you one path. Or I guess it could give you multiple paths too in a way, but you pick one and you stick with one, I suppose. So NP problems, you know, people think that oh yeah, it's because there's so many solutions that makes it NP. No. Again, it just has to do with how long it takes to solve it with the best algorithm we have figured out so far. The next misconception, which is kind of going into what I'm saying because I've been oversimplifying, but the misconception says solving NP-complete problems requires exponential time, which I said that myself. And so first, this would imply that P is not equal to NP, which is still an unsolved question, which is what I said. Furthermore, some NP-complete problems actually have algorithms running in super polynomial but sub-exponential time, such as, and I'm going to write it down here because it's pretty toxic, O to the 2 square root of n times n. That is a problem in sub-exponential time, but super polynomial time. An example of that, and it says here, is the independent set and dominating state problems for the planar graphs, which are NP-complete, but can be solved in sub-exponential time using the planar separator theorem. So don't just assume, even though it isn't most of the cases exponential, there are special cases where something can be super polynomial and still be considered an NP complete problem. Case in point, even I said it a little bit earlier. Take $1 million. Hey, let's figure out together and we'll split the money. How about that? Finally, this is a very popular one, because here's the thing. A lot of algorithms for security rely on the fact that something is NP complete. And so people say, well, if P and NP are equal, which means you can solve a problem in polynomial time that is non-deterministic polynomial time problem, then all encryption and like cryptography is broken, and now all the money's bank is not secured, and financial system will collapse, and major panic will ensue. Well, the answer is that even polynomial time algorithms can be very difficult to solve in practice if the polynomial degree is large enough. So if I tell you, oh yeah, I came up with a solution to a problem, but it's n to the 20th power. Okay, that's polynomial, yes, I'll give you that, congrats. But n to the 20th power for a big enough number, like, not even big enough, like 5? You know, what is 5 to the 20th power? Like, that's a really, really big number. And if we're talking like n is like second count, and each second is n, let me try to plug it in Google. 5 to the 20. Okay, plus 13. So 9.5 plus 13. So 13 digits. So 13 digits would be, let's see, 6 is a million, 9 is a billion, 12 is a trillion. So around the trillion range. Trillion seconds. How many years is 1 trillion seconds? Or 9 of them. 9 trillion seconds in years. That is 285,000 years. 285,000 years. And like I said, I was putting 9, but if I put 95 trillion, as you say, that's going to be a little bit bigger than that. But let's just stick with 9, 285,000 years. If your bank account is relying on somebody having 985,000 years to crack it, I think that's the least of your concerns. If they actually figure it out, because I don't know about you, but that's a long time from now, and a lot of things can happen between now and then. You know, I'm hoping I'm alive, but that's a big stretch. And so, just because something is polynomial doesn't mean it's crackable. And there's a lot of security algorithms that are solvable in polynomial time but that polynomial is pretty big to the point that is not a concern. It's only if you're in mortal where I guess suppose it could be a concern. And you're risking the fact that they may change their password in 285,000 years. Frankly, you're better off kidnapping the person than getting the information from them. But that's a different story, right? We don't encourage any kidnapping or things like that. So yeah. So that's a big misconception, and I like the ones in Wikipedia because they kind of help you discuss things, and so I really hope they spend a lot of time in this in 477. But let's see, anything else I want to say about that? No, I think that's it. So yeah, computing power, it's a big thing. Of course, 285,000 years is talking about if n is 1 second, but if n is 1 nanosecond, things start to get a little bit smaller. So you don't want to 100% be okay with that. But by then there'll be newer algorithms and so on. Just go into the drill and steal the info. Yeah, of course, that's another solution. Frankly, that's a better solution. More fun. All right, cool. So that brings us into the last thing. And that is how to prove a problem is NP complete. Okay? Now, I'm going to very briefly go over this because this is hardcore stuff. Talk about hardcore. And so you use something called reduction. And so first we assume that NP complete is separate from P because we don't know for sure. And we got to take a problem that somebody has, quote unquote, proven to be within the NP complete category. The OG problem of this, the original one, we're almost done, don't worry. The original one is going to be the Sap problem, okay? The Sap problem is the Boolean satisfiability problem. And I'll show you that in a second. Okay, but basically that problem, people have agreed that if NP complete is separate from P, then that is an NP complete problem. And so if you got a problem, by the way, you can put Twitch on your phone and watch it while eating breakfast. I think people did it the first day I streamed, so go for it. But yeah, if you got a problem, okay, that you got to eat breakfast, for example, okay, you got to eat breakfast, and so you need to figure out if eating breakfast is NP complete. Or P. First of all, you can't figure out P, so that is P. So you take a guess and say that it's NP complete. So the way reduction works is you take the problem that you're working with and you reduce it into a problem that is known to be NP complete, such as Sap. How do you do that? You convert whatever you need to do to the input and the algorithm itself. But most importantly, you just convert the input into something that you know is NP. And if that conversion, which is going to take some time, can be done in polynomial time, and then you've converted it into an NP problem, then you can say that it is an NP complete problem. The vice versa could be true. If I could find a way to convert an NP complete problem, if I can convert that problem into a problem that I can solve in polynomial time, and I can do that conversion in polynomial time, then I would have proven that P and NP are equal. Of course, nobody has been able to do that. And so an example of that reduction is the knapsack problem. What is the knapsack problem? And of course, what we're going to do is we're going to reduce the knapsack problem to the subset sum problem, which will then be reduced to the 3-sap problem, which we know is NP complete. Although frankly, people have done this already. So if I had a real problem out there where I had to actually solve something, if I could reduce it to the knapsack problem, then I could assume that it's NP complete already because people have done the other reductions, and this can keep going. So like back to the breakfast thing, if your breakfast involves something that is knapsack related, then your breakfast is NP complete. Get those NP nutritional content. So what is the knapsack problem? The knapsack problem is as follows. You got a backpack, it's the boogaloo or whatever you got, or you have to escape your house because zombies are coming or something, I don't know. And you're trying to pack as many things as you can in your backpack before the end of the world. And you can never come back to your house. So you're trying to pack, your backpack has a weight limit. Let's say it's 15 kilos or 30 pounds, okay? And in that backpack, you can fit 30 pounds, and you're trying to see what you can put there that is going to keep you the highest value, because it might be useful in the boring post-apocalyptic world. So maybe you want to put in some money there, maybe some gold, I don't know, whatever you want to put in there, okay? Maybe some anime magazines for you guys, since you're so into that. Okay, maybe you value that high in the bartering world. So yes, okay. So anyways, so you go ahead and you say, yeah, toilet paper. Actually, yeah, toilet paper would actually be cool because it's very light in weight. So that actually could work out pretty well. So you have your backpack and it can only take 30 pounds. And you have toilet paper that is maybe 1 pound. And we're ignoring dimensions, but that would make the problem harder, but it's the same thing essentially. Toilet paper, which is 1 pound. You know, you got gold that is 5 pounds. And let's say toilet paper is in post-apocalyptic world is $100, whereas gold is worth $800 for that 5 pound blob. And maybe the anime magazine is 8 pounds and is worth $800. Okay? Yes. Well, oversimplification unless you want me to do fractions here, okay? Yeah, it's heavy duty stuff, all right? You don't know what you're going to be eating in the post-apocalyptic world, so you need some heavy duty stuff, okay? So, anyways, how do I most efficiently store things in my backpack for the most amount of value? Okay, well, the greedy way of doing this is go with the biggest value item, put as many of those as you can, and then top it off with the lower value ones. And maybe to make things different, we'll make this like $700, okay? So, okay, let me go ahead and put a bunch of the anime magazines then. I can put in 8 times 3 is 24, right? And 8 times 4 is 32. So I could put 3 of those anime magazines. And now I'm at 24, okay? And then I could go ahead and put in a gold in there. I could put in 2 golds. I would be overweight. So I could put 1 gold, which adds 5, which brings me to 29. And then I could put 2 toilet papers, which adds me to 31. But is this the most efficient solution of this? The answer is no, because the gold is lighter, so maybe I should have gone with that. Okay, so I can go with the gold. I can go and put in 4, 5, 6 of the gold packs, which would get me to 30 pounds, and then put 1 of the toilet papers, which would get me to 31. I think that's the most efficient one, but that's because this is an easy problem. But the more mixture of items that we add in here and the more factors in, makes it a much harder problem. This is actually an NP-complete problem. If I tell you code a solution in P time that to do this problem without any heuristics, which is any guessing, which means I need it to always work, like every time, 100% of the time, you could do it. You could code it. But what I would do is probably I would brute force it because I don't know. I mean, I could go on Geeks for Geeks and refresh myself on some of the ways to solve this. Probably dynamic programming would actually help me a lot. But I could not code this in an algorithm whose time complexity would be P time. It would have to be exponential time. Why? Because I have to check all these different possibilities to get it working. And so that's a knapsack problem, basically. Okay, so maybe you could calculate the ratio of weight value to determine which one to put knapsack. You could do a lot of things, but you're still going to be talking about NP time versus P time. And that's the reality of things. Such a simple problem is so hard. I heard people talk about traveling salesman problem. Same situation, I think. Okay, so we want to prove if this problem that is known as a knapsack problem is NP, right? I think it is, but how do I prove it? Okay, well, I need to simplify it to something else that I can more easily get proven that is NP. And that is going to be the subset sum problem. That one is, given a set of elements, find a subset of them whose sum adds up to a given number. Which means if I have a bunch of numbers in a list, no duplicates and no negatives, and I add them together, can I get up to a specific number? So like, if I have 1, 2, and 3 here, and I want to get a 25, can I combine these numbers in a way that I can get 25 out of that? Yeah, I could do like 3 plus 3 plus 3 plus 3 plus 3 until, what is it, 3 times 8 is 24, and then plus 1, which is 25. So I could do that. I could also do like 1 plus 1 plus 1 plus 1 plus 1. So I could do that, but I have to do it for all combinations, right? That would take me a long time to find all combinations and things like that. And you can see that that's kind of related to what we're doing here, right? The same math. So you can see that these problems are very related. How do I convert this problem into this? With a polynomial time conversion, where I probably just simplify this into just math, right? I get rid of the whole idea of toilet paper and money, and I just stick to just math. I convert it into that. Of course, I don't want to do that. I spend a lot of time doing that, and I'm not even sure I could do that off memory. Okay, once I have it here, I'm going to simplify it even further. Okay? Yeah, this gets into combinatorics actually. Into what is the OG NP complete problem, which is the Sap problem. And there's different layers of this. It's actually a 3-step problem. We're just going to talk about the first Sap, the most basic Sap problem. I talked about it already in class before, but I'm going to refresh your mind on it. And that is the Boolean satisfiability problem is that given a Boolean formula, such as like a little if statement that I have here, does there exist an interpretation that satisfies it? And by that I'm saying, if I ask you right now, what values do I have to put in, and I want an answer, chat, what values do I have to put for A, B, and C so that I can get the sectors clear output? And vice versa. What outputs do I need to put for A, B, and C to get the not clear output? So, chat, what do I need to plug in to be able to figure out what this code is? And can you ever even output either of these? I should have done a poll and they can see people responding, but that takes too much time. What does that mean? I mean, what do I put for A? True, false, or not true? Like, what do I want? I want this to evaluate to true. I see there's no way to answer electronic at all. Well, yes, kind of getting to that. So we get true, true, and false. All right, so true, true, and false. And I'm going to assume that anything other than that is going to probably give me false. So let's see if that works. True and true is true, or not true. That's okay. The true perseveres there. B or C, true from free works out. T and B, that's good as well. T and then the true and another true is good as well. And then the false there is good as well. So you guys are indeed correct that the answer to this is true, true, false. If I flipped my C to true, then this would evaluate to false. So I suppose that would be the solution if I wanted to get the not clear output. Okay, notice how easy it was for me to test whether or not this was the right answer. I just had to plug it in. You guys had to do the hard work of trial and error trying to get this going. I think somebody says that false, true, false will work too. Let's test it out. False, true, false. That's not going to... Oh, you know that? Yeah, that works on that part. Okay. And then you said false. What was it? True and false here. So that works okay too. And then true and true works okay. Yeah, and then false. Yeah, so that is indeed another solution. Congratulations. For a second, I thought you meant fix that for you, like Y. Okay? And then I don't know what the X part means. Oh, it's irrelevant, you're saying? Yeah. Yeah, good point, because that makes it irrelevant based on this. So, yes. Okay. So, we have found two solutions so far. Are those all of them? I don't know. You'd have to pretty much brute force this to get it going unless you know a better way. And so this is what I'm getting to. This is a very, very hard problem, even though it's super simple. Like, yeah, it's just an if statement. Super simple problem, but very hard to actually find a solution that always works, like an algorithm that always works and could solve this in polynomial time. And so this is why this is an NP complete problem. So how do I simplify subset sum into the Boolean satisfiability problem? Well, again, I'm going to hand wave and say that I'm not going to talk about it because it's going to take a long time. But ultimately, it is possible to do. And computers technically do it when you're coding something because they turn everything into Booleans, right? You can convert a multiplication into Boolean operators using and, or not, right? You all did that if you took CP 100. You can convert like you can look at a multiplexer and things like that. You can make any math operation in binary just using a truth table, which is how our CPU works, basically, logic gates. And so that's kind of what's happening here as an oversimplification of how to convert the subset sum into the satisfiability problem, per se. Okay? And if you can do that conversion in polynomial time, which is another trick part, because otherwise I could say anything can be converted into Booleans, therefore everything is NP complete. Well, first of all, you can convert just P is a subset of NP. So you can always find a NP complete solution to a P problem like Bogosor, for example. That's That's like on the level of like NP hard or something, right? It's not polynomial solution time. However, it's a polynomial problem that you could solve using something like quicksort, but you can also go really hardcore bad and just run it in like NP time. Okay? You guys are still talking about that. But anyways, so that's pretty much it. I hope you guys had a brief introduction into the world of algorithm analysis in the sense of P versus NP and how all the algorithms we talked about apply in the bigger picture. I want you to not just memorize these things like APL and regurgitate them. I want you to understand why they work. And so when you learn more algorithms, you apply the concepts that you learn, such as divide and conquering, a little bit of dynamic programming, which you're still fresh on, but you kind of get the idea of remembering outputs as you go on so you don't recompute them. And all of those things can really help you to solve your problems in a much more efficient way. So when you're actually creating your own algorithms, you're not trying to reinvent the wheel. And so with that, I'd like to remind you that your final exam is indeed tomorrow from the high noon to the high moon, from 12 p.m. to 12 a.m. I wish you the best of luck with that. But more importantly, thank you all. I know you all are hurt because I said you're not smart or whatever, but I will tell you this. This was the funnest combination of 202 and 302 I've had in a long time. Or ever, actually. So I appreciate you guys for being a really good crowd and really good people. And I'm kind of going to miss you guys when you guys go over the break. But maybe I'll see you guys in 219. So I wish you all the best. I mean, of course, you guys still got to do the assignment. So it's not like this is the end of everything. But this is at least the last time that you'll see me. Unless you watch a video again. So I had a lot of fun, guys. It was great, you know. There's a lot of you in that class who are really, really smart, you know. But more importantly, it's not just about being smart, but about being good people. And I think you guys are really good people. And I know you guys will succeed when you get out in the workforce once this whole craziness happens. But in a way, you got lucky that it's happening now and not when you're trying to get a job. Like people who are graduating this semester kind of have it tough, right? Because then at least you're in school and that keeps going versus like, you know, if you graduated, then what happens now, right? So there's that silver lining in that. You know, focus on school, let the world do whatever it has to do. Hopefully by the time you graduate, things will be a lot cooler. But if not, computer science is a great job to do from home. So I'm sure that you guys will have no problems getting a job. I wish you all the best. Feel free to contact me and stop by my office at some point. I know some of you already do. And yeah, I'll change your status to vets if you pass the class, which, who knows, right? Like, it's still up for grabs. Although, if you're in that nasty situation where you got a low C or a D, you can't always switch it to the S, right? So there is that help from the university for that. It's only really you're at risk if you got an F. So if you're in that category, do your best. Because if you get to that D, this semester you got that luck that you have the S to save you. S for save. Get that assignment done. And thank you all. Yeah, I mean, you should be scared of failing. The final is not cumulative, but it's still a test at the end of the day. Yes, don't forget to turn in the assignment and don't forget to do the final exam tomorrow, more importantly. I had a lot of fun. Am I ever going to reach the final once it's graded? We'll talk about it on Discord. Why not? So like tomorrow night, I can talk about it. And as for graded, I don't know, because it's probably going to be rushed before the end. So, I mean, I'll try. I'll do my best. You know, if you're around Discord, then you'll get to hear it. S for saved when they ask you that. I dance, but I'm not a good dancer, so I don't think I like dancing at all. What about the assignments? Since there will be no Turing next week, will your TS be around? I do believe they'll be around, and if not, I'm going to be around. I have nothing else to do for the next 3 weeks, other than preparing for future classes. Like I'll be around, so just in the strange hours. But my sleep schedule is actually good now. I wake up at 2 a.m. and I go to sleep at 8 p.m. So, or 7 p.m. So I'm almost back to track. Not the semester's over though. But oh well. That's it. All right. That concludes the lecture. All of you, you can go away if you want to. I guess if you have any questions in the final or anything like that, you can ask me. Otherwise, I'll hop on Discord. Make a Valorant program for your kids. I might actually take some of that CSGO, some of the assignment 12 code, and give it in CS202 and 135 over the summer, because I feel like I spent so much time on it. I might as well recycle some of it. Like maybe make them render the map, or make the car map class, or give them pieces of code and make them do like projectiles in 202, you know. Can I do another quick DFS example? Yeah, sure, I could. I'll do that in a second. See you in 219. Yeah, for those of you that are taking 219, I take remiss in the fact that I'll see you guys again. Because, like, I actually do get sad. Because, like, the Discord just goes super quiet over the fall break. Like, on the winter break. So I was like, damn. And I was probably going to, like, fade away too. Give Inception to scare them. No, Inception's probably on the internet already. That's a gone assignment now, sadly. It's a great assignment, but it's gone. For those of you that are taking 218 next semester, don't worry. I'm sure by the time we get to 219, you know, you'll be good to go. Who knows? Maybe I'll teach it again. Maybe not. I don't know. By request, I guess. Did I switch it to the remote? Oh, important, I suppose. If you are in 219, we are going to do the remote. So that's going to, you might actually, oh, I should say this. If you're, on the serious note, if you're taking 219 in summer 3, I do think that they're going to cancel the class and relist it as a remote class. So you may have to re-enroll. So beware, because the class is full and I don't want you guys to lose your spot. And if you do lose your spot and you were enrolled before, send me a message. And it's a lot easier to add people online than it is to add them in the classroom, because like we don't have a fire code. You know, as long as Twitch can handle it, we're good. So that's a sort of a solution. But do keep track of my UNLB. And if you see any change, post it on Discord, and I'll send out an email to everybody. Well, that was summer 2, I think. Summer 3 is a little bit different. I heard from Mario, we have to cancel the class and relist it again. So it's possible you get kicked out of the class. Because, you know, they want you to be aware. You don't want to get scammed. That like you sign up for something and get switched, right? Am I the one grading the final? No, the TAs are, unless they disappear. Either way, for the people that are still here, you get a little hint. That pseudo worksheet that I did on Tuesday, it's very, very close to the final. Like almost like question per question basis. Like if you follow lecture on Tuesday, you should have no problem in the final. I mean, I do have some like theoretical questions at the end, and I have the stuff from today. But the big stuff, which are DFS, BFS, MST, both of them, Dijkstra, topological sort, those algorithms that we did, that's the big stuff, right? If you can do that, you should be fine. Yeah. Which was, I mean, like we basically did like a worksheet. We did problems, like we basically did all the algorithms, right? Which is what the test is. Like, no surprise there. Midterm 2, you had to do AVL, you had to do hashing, you had to do like building a tree from the traversals. Like those were all algorithm-based questions, right? Same thing here. Oh yeah, do your course evaluations regardless of what your rate for, and do it for everybody, not just for me. Do it for everybody, because I know that some of you had some serious problems with a lot of people in other departments, and you gotta voice your problems, otherwise nobody knows. How many questions on the final? Yeah, well, I said there was gonna be about 10, but there's 14. Because like one question was like, I split it into 2 to make it easier for grading. And then there's like a lot of little tiny questions, like for the ones that I said I was gonna ask them, like conceptual graph questions, right? Let me think of something that's not on the test that I could ask you based on that. Well, no, I'll think of something from midterm 2, like the height question, like what is the height of the grandchild routes? Even that is harder. These are more basic than that. So there's there's like tiny questions, but the point distribution is making like I'd say like 80% is all the algorithm stuff, and then 20% is like the little tiny questions. And I did put some memes on the test, but I didn't put any meme pictures this time because I didn't want to confuse people between the graphs and the memes. Are they all upload problems? They are, except for the theoretical graph questions that I asked at the end, and a disjoint set question I asked. So for that, you can do the thing that people suggested, which is like, you can either upload per question like last midterm, or you can do one upload at the end with everything. So you have that choice, because I know some people had problems with individual uploads. Like, I guess it took them more time. I don't know why, but it did. But maybe the scanning app, I don't know, because they had to split them up. But yeah, you have the choice. So you can either choose to upload everything at the end or upload as you go. Please don't do like 50-50, like start going one by one and then switch over to everything at the end. We already had issues with the TAs got confused and they didn't grade that the last page with the extra upload stuff. I corrected that stuff, but we don't want to have that situation. So be very clear about which method you use. Like put it in big font or something. And the ones you should do by essay though are the non-upload questions. I don't think any of those require a picture. And if they do, you can put it in the file. But yeah, if you don't like the individual upload stuff, yes, you can put it at the end. I put that on the explanation and everything. You will get the access code for the test tomorrow on the message that I already preset to send. That way, if I'm dead, the test will happen regardless. But yeah, you guys will figure it out. I guess I'll put it really fast here. I mean, do you really want me to do an actual example now? Imagine doing an example in a class. How about that? BFS. Q's are involved. Okay, pick a node A as a start. You have your visited list here. Wow, that didn't work out. There we go. And by the way, I did keep, I think the biggest graph is like 7 nodes. Because I wanted to make sure that you guys don't have to draw a million pictures. You still gotta draw a lot of pictures, but at least it's not like 20 vertex graph. How much time do you get on the test? 3 hours, just like midterm 2. I took the test. I will not tell you how long it took me, because the fact of me telling you how I timed it would be a bad thing. I'll tell you after though, the test, like when the test finishes, okay? So, how the TA's taking the test, they didn't take it this time, but I told them to take a look over it. So we'll find out. But I took the test, like I said. I just can't tell you more without giving away too much per se. Okay? No, please. It was I wish I could tell you the time, but me telling you how I've timed it is a bad thing, because then you will know things. So. And I did make the test, which is quite an unfair comparison too. So like, you know. All right, I'll finish this example so we can end. I need to check Discord if there's anything. Nope, nothing on Discord. Okay, so I guess I'll do this really fast. You gotta push B and C to the queue. Again, stick with that alphabetical thing. If you don't, it's not a big of a deal, but you know, BFS, because they wanted me to do BFS. So B and C, and then add A to the output, mark that as visited. Next thing you know, you pop out the B, add it to your output because it's not been visited yet, and then add whatever's coming out of that, which means you're going to add the D and the C, but not the A. I guess as we're sticking alphabetical, we'll go with that. Again, you don't add the A because you've already marked it as visited, okay? So that's a big thing to remember. Okay, we're done with B, so we can mark it as visited. We get the next thing out, which is the C. All right, the C has 3 edges, D, E, and A. However, you do not add that A edge because you already marked A as visited. You do add D again, and you do add E. Let me move the Q down so I don't run out of space. And then you can go ahead and mark C as visited. You don't add B because you've already visited it. Same with A. Okay? All right, the next thing you pop out is another C. But because you've already marked C as visited, nothing happens, you throw it away. Next thing you get is a D. The D you haven't visited, so you add it to your output. So don't forget I'm going to mark it as visited already, because I keep forgetting that. And then check all the edges that it's connected to. In this case, we got the F there, so we're going to put F in our queue. We do not put B or C because they both have been marked already as visited, so that's all we do. Okay, at that point we can move on and dequeue the next thing, which is going to be another D. But here's the thing, D has already been marked as visited, so nothing happens. You don't add it to the output, nothing. Okay, we got E and F. We're going to pop out the next one, which is E. In this case, E has not been marked as visited, so we add it to the output. We mark E as visited because otherwise we'll forget probably. And then we add all the edges coming out of it to other vertex, which in this case are E to C and E to F. E to C has been, well, that's a big delay if you just said that. But yeah, E to C you don't put because C has already marked as visited. F you do put because F has not been marked as visited, even though it's already in the queue. That doesn't matter, you throw it in. Okay? At that point, you can go ahead and get that last thing out. So get that F, mark it as visited. Nothing gets added because D and E have all been marked as visited, so you're done at that point. Then you take out the next thing from here. Of course, you've already marked F as visited, so nothing happens. When your queue is empty, that is your quote-unquote queue, that you're done. Also, the fact that you marked everything as visited was another queue that you were done. But that's queue as in queue. See what I'm doing there with the language? So you show your queue at each step? Yes. And if you don't want to draw it like I did, you can do it horizontally as well. Just show what's in your queue after you finish each vertex per se. You don't need to say like, oh, I inserted one thing and then draw it again with the second thing inserted. No. Just be like, after I visited this node, this is what's in the queue. And then this is what's in the queue. And then this is what's in the queue. If you look at the Tuesday lecture at what I did there on paper, well, tablet is exactly what I want you to see. In fact, in the test, I didn't want to like spend too long making the questions too wordy. So I said, show your work the same way I did it on Tuesday lecture. That way, you know, if you're confused, you can go and look at that. But I wouldn't recommend you do the middle of the test because that's going to waste your time. So just make sure you watch the Tuesday lecture. Like literally, that's my advice to you. We did that pseudo worksheet. We reviewed every problem that possibly could show up in the test, except for like the theoretical graph things. And even those we talked about a little bit. So that's like your Bible for the test. Can we just cross out stuff when drawing on paper? You can do some crossing out, but you're going to hit a limit where like I'm going to be confused or the TA is going to be confused. So you be the judge of that. Do you show the visited full array? I do, but again, you just check mark it. That's why I like Paint and things is nicer because you can just copy and paste it so many like as you do it. But if you have to do it by paper, then yes, you can also keep it like a list of like visited, and then just write the ones that you have visited, and then just keep adding to that. That way you don't have to write like a box with check marks and, you know, art, basically. Can you do DFS? Okay, let's just do DFS on the same graph. Shouldn't be a big deal if I erase this, because, I mean, it's on the video, so you can screenshot it, you know, with Twitch. Okay. Again, from A. So, in this case, we're going to change this to a stack. Okay, stack time. So in this case, we add A again and we mark it as visited because first thing doesn't change whether it's BFS or DFS. Just like prim and Dijkstra don't change for that first vertex. They're going to be the same thing. It only changes after the second one. Okay. In this case, we are going to go and add B and C to our stack. Sorry, I had to think for a second how to do the algorithm. So yeah, okay, it came back now. It's all in here now. Okay, so B and C get added to the stack, and then you're done. Okay, all right. So next thing you pop the next thing from the stack. And you add it to your output if it has not been marked as visited. Okay, from there you have A, C, and D that are looking there. Let me do a different color now. So A, C, and D. Okay, A has been marked as visited, so you don't mess with that. Then C and D you do add to the stack. So I'm going to add C and then D. Again, this stack, you know, first in, first out versus last in, first out. Stacks are going to be your last in, first out. First in, first out is your queue. So this is last in, first out. I might have said backwards in the beginning, so I don't know. In case you guys confused on that. You guys know that. Stacks, trivial stuff. Can you label top and bottom? Yeah. I know that looks weird, but some people do theirs the other way around. I don't know why I do them this way. I mean, this is like the opposite of you can think of this as like where I'm putting in the plates. So I know for people they think of like, yeah, I'm gonna put stacks like that, but I don't know why. Just the way that I like drawing them. I guess I'll close this. That'll make it less confusing, and maybe open the bottom. Yeah. Okay. So we added C and D, and we mark it as visited, and we're done. Don't forget to mark it as visited. I'll be honest, I forget that sometimes. You've seen it on the lectures, right? I go back and fix it, but like, you know, I fix it before I make a mistake. But if you don't, and you do make a mistake, then things get nasty. That's more like those cup dispensers and stack of plates. Yeah. In this case, it's actually like a yeah. That's a good one. Yeah, cup dispensers. Yeah, like the ones you take out. Like in I haven't seen those in a long time though. I've seen the ones where they put the cup of the plastic top of the cup. I've seen that. Okay. So anyways, we go ahead and pop out the D and throw it in there because it has not been marked as visited. And we're going to go ahead and add in from there. So we got D, C, DF, and DB. But you don't add DB because it's been marked as visited. So you just add C and B, C and F. So C and F. Okay? That's it. Nothing else. Make sure you mark it as visited. Okay, moving on. We're going to take out the next thing. It has not been marked as visited, so we are clear to add it to the output. Mark it as visited now, so again, don't forget. And then you look and see, so it's connected to D and E. D has been marked as visited, so you don't add it to the queue. The only one you're going to add to the queue is going to be the E. I said queue, I meant stack. Sorry. Okay. Good. Didn't used to want in alphabetical order? Yeah. I did go in alphabetical order. Like, you add it to the queue in alphabetical order. Or you add it to the stack in alphabetical order. But because the stack is backwards, it's technically not in alphabetical order anymore. See that? I added, when I was in B, I added, oh, I see. When I did, when I went to B, I added, no. Because here's the thing. Okay. When you get to B, you add C and D in alphabetical order, right? Which means you add C first and then D. But because it's a stack, C gets deeper than D. See? You put in C first, and then you put in D. So D is the top of the stack now, which is why I went to D next. Next, when you get to D, you're gonna add in C and you're gonna add in F, right? So you add C first because it's alphabetical, and then the F. So F is the front of the stack. That's why we got to where we are now. So we went ahead and we did F. So even though I asked alphabetical, because it's a stack, it's actually going to go backwards. If it was a queue, then you would see it go alphabetical. So you wouldn't go from A to C because B is on the top. Yeah, because you add, so in the start, you have A. And you add B and then C to the stack. So B goes in, but then gets pushed to the back because you add C. Because of that, C is at the top of the stack. So C is at the top, not B. Because you're adding it alphabetically. Think about it this way. If I have a list of numbers, and I add them all to the stack, and then I pop them all out, I get the list backwards. Oh, I see what you guys are saying. I did go to C. Yeah, my bad. Apologies. I can see what you guys are saying. Yeah. I don't know. At some point, I decided to go to B instead of C. My bad. But anyways, had I gone to the C, you would have gotten a different alpha. So just keep going with where we are now. But yes, I can see what you're saying. Probably in the beginning, I should have gone to C instead of B, but it's still valid. That's what I'm saying. Try your best to go alphabetical. If you screw up, I'm not going to deduct points for it. I'm just saying it'll make the TA's life harder and a higher risk that they're going to grade it wrong. So we should be good. Okay, anyways. All right. Finally, we get to the E because that's the latest thing. And nothing gets added at that point. Oh, no, we still got to do C, actually. So E does add another C to the stack then. And as you can see, we got a bunch of C's in the stack now. So we're going to pop one out, and it's going to go there, and then the rest are going to pop out. And nothing will happen. So done. See, I like the fact that this is live and you guys can interact with me like that. Otherwise, I would have just gone on. All right. Anything else, or are we good to go? Can we do topological sort? You want to see topological sort? Okay. I guess I'll sort first. Why not? That's an easy one. View dots for like Dijkstra. That's when I would have grumbled. I don't know if there's a cycle. I'm just kind of drawing as it goes. Okay. Are there multiple outputs for the test for DFS that are acceptable then? I mean, here's the thing. What I do tell you in the test is which node to start with. Like I tell you, start on this node. That reduces my possibilities of grading by a huge amount. I learned that the first time I taught 302 when I just said like do a DFS, and I was actually grading the test that semester, so like not fun. But anyways, now I actually I tell you which vertex to start on. But yes, even then there can be more than one answer. I do recommend, I say there like, yo, please go alphabetical, less possibility of differences. But of course, if you make a mistake like I did, it's fine. You know, statistically, maybe 10 people will do that. 10 is better than 90 or 70, however people we have left, which means it's still less variety of answers to grade. And most of the time, like, if you see a different answer and you check it and it's right, you use dynamic programming to remember that that's a good answer. So that way you don't have to recompute it every single time you see it, right? So you just start making a list of possible answers. But yes, in fact, for this graph, like if we ignore the alphabetical stuff and we start with A, there's like, that's one answer. That's another answer. And then you go back all the way here and do that. So over there you can see 3 answers. So yes, there's tons of answers for this. It really depends on how you put things in the stack. Okay, topological sort. Here we got a topological sort. Again, in this graph, there's only one place you can start actually, which is this one. You can only start in places that have an in degree of 0. And I think this is the only node that has an in degree of 0. If, however, we had something like this, then you could also start here. At which point there will be multiple answers. In the test, I can't remember if I tell you which node to start on, or if there's only one node to start on and I don't tell you because it's kind of obvious. So just go with the flow. Okay, so in this case we're gonna start with A. Why not? So we do A, and then of course you redraw the graph without it, like that. Of course now I can just erase it, but you would just copy and paste it. This only works for a cyclic graph, right? Yes. And we are about to find out if this is a cyclic or not. I didn't think about that, but we'll see. Okay, next you got B to remove, so remove B. This is the one algorithm in the entire test where it's mostly just drawing pictures. There's no stack, there's no queue. You could do this the data structure fancy way, but if you remember, if you notice, I didn't really cover too much about the algorithmic way of doing it. I think I may have done that on the day of the lecture, but I told you don't have to know it. So yeah. Yeah, we'll say that. And yes, it is quite a useful way to tell this cycle. Yes, either this or disjoint sets. All right, C is next, because that's the only one that can kind of have an integrity. From here, D is next. Get rid of that. You know, I kind of wanted to have the graph here. So hold on a second. Gasp. No, now I can't back out. Graph is gone forever. Oh well. Watch the video. Anyways, D, G, which gets rid of those, and then at that point, there's actually, I'd say, 3 answers to this possible graph. This is one of them. This is another one, and this is another one. Actually, there's more answers than that. Combinatorics. One of the answers could be E, F, H. Another answer could be E, H, F. It's binary, so I think there should be 8 answers. Do you want us to write a possible solution to the exam? Read the question. If it asks you to write more than one answer, do it. If it doesn't, then just answer with one. But everything is in the questions. And yes, is there? I was going to say, yes, there's a trick question, but I can't remember. Yeah, there is. There is a trick question, yes. I remember that. There is a trick question, so if you see something sketch, probably is. It's my first time joining the stream. We are actually about to finish the stream. It's the end of the last class of the semester. Data structures. We'll review for the test they have tomorrow. All right, I think that's it, guys. If you have anything else, just send me a message on Discord. And again, I wish you the best. What if there is no trick question and that's the trick? Maybe. I actually do think that it's super easy, the trick question, because of things that I can't say because otherwise it's bullshit. Like it's gonna be like super obvious. So yeah. It's actually related to today's content, so there's that. So yeah, you can already guess. Don't even. Yeah, I'm not saying anything if I see you on chat. But all right, guys, I am gonna miss you. I will be in touch in Discord. I do want to. Maybe I'll make a video of the game running once I fix my VM. So that's it. There are no answer questions or things like that. So yes, stay safe, everybody. Don't get COVID-19. And if you do, then stay healthy. Yes, we should play some Valorant sometime. But for now, test study time. I'll see you guys all. Stop by my office sometime. Say hi to me. I'm not going to disappear. I'm going to miss you guys. I had a lot of fun. This was actually quite an experience for me. Wouldn't have even guessed it a million times in the world that at the beginning of the semester, at the end, we were doing this on Twitch. So I really thought the YouTube thing was going to work. When you guys said Twitch, I was like, this is a meme. Why would we do Twitch? But frankly, Twitch worked so much better than YouTube. So except for the ads. That's toxic, but GG's. Stay safe. I'll see you all on Discord. I'm not going anywhere. So this is not goodbye. But it kind of a little bit is. So all right then. I'll see you all on the other side. Good luck tomorrow, guys. Good luck tomorrow. See you pretty soon. I love you all.